Fish weighs 40 newtons. We just said to find that force of the scale, that is mass times acceleration in the y direction plus acceleration due to gravity. So if my fish weighs 40 newtons, could I find the mass from that? Because remember, weight is a force, not a mass. So if I have 40 newtons, I know that weight equals m times g. So 40 newtons equals mass times my 9.8 meters per second squared. So to get mass, I would just take 40 divided by 9.8. So if we did that, we would get 4.08 kilograms. So I have, this fish is 4.08 kilograms, which would be about 9 pounds. That's a big fish. So we have 4.08 kilograms for the mass. So I know mass is 4.08. And they said the acceleration in the y direction was either a positive 2 meters per second squared or a negative. So let's just do the positive version first. So I have a positive 2 meters per second squared plus my acceleration due to gravity. Okay, so if I do this one, I'm going to get my spring scale to read 48.1 newtons. So the weight of the fish was 40, but now we're accelerating, the elevator is accelerating upwards, which means that the fish is also accelerating in the upward direction. So because of that upward acceleration, the scale actually reads greater, which is what we said based on showing this spring scale equation up here. If this is positive, the spring scale should show a greater weight than, should show a reading greater than the weight of that fish, and it does. So let's do it in the opposite acceleration. So instead of a negative, or instead of a positive 2, we want to make that a negative. So if we do that instead, we will get our spring scale to read. So if we have our negative 2 plus 9.8 times 4.08, that would give us, I think, 31.8. Yeah, 31.8 newtons. Okay, so now in this case we said if acceleration was in the downward direction, then acceleration would be negative. So my spring scale should read less than the weight of the fish. So again, the weight of the fish was 40, and now the spring scale reads 31.8 newtons. So that checks out as well. Okay, I want to do one more example here, and I want that one to be with something called an Atwood's machine. Now, when two objects of unequal mass are hung vertically over a frictionless pulley, and let's assume that the pulley also has negligible mass. We know it has mass, but we're just kind of taking it out for now. The arrangement here then is called an Atwood's machine. So I have two different masses here that are connected to some pulley system, and we're just not going to consider the pulley situation, or the mass of the pulley. So I have these two that are connected by the string. So the tension in those should be the same, right? But their accelerations are going to be in different directions. So let's say that this mass is lighter and this is the greater mass. This mass would be accelerating upward. This mass would be accelerating in the opposite direction. So we have to think about these two masses as two different objects. So I would, every time you see an Atwood's machine, I would think about them as being completely separate, which is what we see here. So if I'm looking at mass 1 here, it has a specific weight force, and it also has tension. But since this mass over here is larger, this mass is going to be moving upward. So the tension should be greater or exceed the weight force for it to move upward. mass number 2 is larger, so it should be moving down. So the weight force here should exceed the tension force of that string or of that rope. So based on this picture, I want us to determine the magnitude of the acceleration of the two objects, and then also let's find a general equation for the tension in that lightweight string. So I want to find acceleration of the objects and tension in the string. Okay, so like I said, let's break that up into object 1 and 2. So object 1 would be mass number 1, and we knew that that one was moving upward. So we know that one's moving in that positive y direction. So let's draw our free body diagram for that. We had the tension and then the weight force, but let's break that one down to be more specific since this is mass number 1. So we know weight force is equal to mass times acceleration due to gravity, so let's say that's m1g. So the mass of that first one times g. So here's my first object, and this one should be larger because it's accelerating upward. Then I look at the free body diagram for that second object. So I have weight, and again I have tension. So there's tension, and then my weight force should exceed the tension force because that one was accelerating that way. So let's actually write acceleration, acceleration. Okay. So we know that we only have y direction forces that are taking place in both of these objects. So first let's write the net force for object number 1. Which is just mass number 1. So I'm looking at this one here. I know that the net force in the y direction would be tension minus the weight force, or m1 times g. But since it's accelerating, I know that this wouldn't be equal to 0, it would be equal to the mass times the acceleration in the y direction. That's going to equal tension minus m1g. And let's designate that's also m1. So let's rearrange this so that way we have it, tension is equal to these things. So tension here would equal m1 times acceleration in the y direction plus m1 times g, which is the same thing as saying m1 times ay plus g. Okay, I want to do the exact same thing, but let's do this for object 2 now. Okay, for object number 2, I want to write the net force in that y direction, since that's the only direction that it would be accelerating in. So in the y direction, remember that this is accelerating downward. So if my acceleration is moving this way, I could say then that this way would be that positive y direction. That's what I'm going to call it. If I'm accelerating downward, then I'm going to say that that movement is positive. If that's the case, then I would have my weight force, m2g, minus tension. And it should be opposite to number 1 because number 1 is accelerating upward and then that second mass is accelerating in the opposite direction. So they should be opposites. So I have my weight force minus tension. This is also not equal to 0 because I have